Chemical kinetics is the name used for the study of the rates of reactions. Most chemists just call it kinetics. The rate at which chemical reactions occur varies widely, and there's enormous repercussions in terms of apparent stability or cost of production of some materials. Take, for instance, the case of a diamond. A diamond is an unstable form of carbon which is slowly turning to another form, graphite. However, the process is so slow that at room temperature it would take billions of years for a diamond to completely turn into graphite. So nobody's really worried about it. At the other extreme, there are chemical reactions that are complete in a tiny fraction of a second. I should warn you, this is one of the fastest chemical reactions known to humankind. If you blink, you will miss it. Here we go. Measuring the rate of a reaction at these extremes is tricky. However, there are lots of reactions that occur over much more sensible timescales, like minutes or hours. We'll be considering those. In some ways, measuring the rate or speed of a reaction is no different to measuring the speed of a car. If we plot the distance the car has moved as a function of time, the speed of the car at any point is equal to the gradient of the graph. We can do the same thing with a chemical reaction if we plot the concentration as a function of time. However, we need to be careful here. Whilst it is possible to monitor the progress of a reaction by following the production of a product, since the rate of a reaction is often linked to the concentration of the reagents, we normally study rates of reactions by following the concentration of a reagent, not a product. And this changes the graph somewhat. As the reaction proceeds, the concentration of the reagent will decrease. Hence, our graph will have a negative slope. However, a negative rate would imply that the reaction is going backwards, which is not the case. So now we can say that the rate of the reaction is equal to the change in concentration of a reagent divided by the time for that change. But we include a negative sign to ensure that the rate quoted is positive. In our car example, to calculate the speed, we divided distance by time to get an answer in miles per hour. Using the same logic, calculating the rate by dividing concentration in moles per litre by time in seconds yields a rate in moles per litre per second. Now, for some people, this is all they need to understand how rates are calculated. However, for the rest of us, me included, an example with numbers helps. So here we go. Here are the results from a kinetics experiment. I'm not going to complicate things by showing the details of the reaction. I just want us to concentrate on getting the rate. We can plot the concentration as a function of time. Few of our measurements appear to have some errors associated with them, but that's fine. We can draw a line of best fit through these data points and then take our data to calculate the rate from that. By doing so, we hope to average out the errors. So let's draw a triangle to define the numbers we are going to use from the graph. Over this region, the concentration goes from 0.41 to 0.05 moles per litre, and the time goes from 200 seconds to 1000. The change in concentration is calculated by subtracting the earliest concentration from the later one. This gives us a change in concentration which is negative. This is correct. The concentration of the reagent decreased during the reaction. Change in time is calculated by subtracting the earliest time from the later one. This gives a positive change in time, which is correct. We were monitoring the reaction as time progressed. Hence, our gradient of the graph is calculated to be minus 0.00045 moles per litre per second. Because we are monitoring the progress of the reaction by the decrease in reagent concentration, the rate is the negative of this value. So 0.00045 moles per litre per second. You'll have noticed that in this case, the rate of the reaction doesn't depend upon the concentration of the reagent. The reaction occurs at a constant rate until the reagent is completely consumed. This does happen, but it's fairly unusual. So what happens if the rate is dependent upon the concentration? Well, for a start, the graph we drew today won't be linear, but that's the subject of another video.